Okay, everybody, welcome to our second lesson for the EECS education series. So today we're going to be going over a high-level EECS diagram. This isn't fully exhaustive. There's a couple PCBs missing that maybe we might dive deeper into later. I have some of those listed at the end if you're interested, but this is meant as sort of, I walk up to the car, and what do I do to turn the car on? It's sort of from that point of view. So we're going to be walking through that. And if you have any questions, it'll probably be best if you interrupt me during the presentation and just ask it then, because it is kind of a flow. So just unmute and ask any questions during the presentation. So without further ado, why are we learning about this? It's important to know what happens when you turn the keys on for the car and what process that's actually causing inside of the vehicle. Sometimes it can be a lot like a black box if you're just touching things on the outside and you don't know what's happening. So it's important to know like what the internal state machine of the car is doing. This also gives you a high level overview of how we divide the functions of each of our PCBs and also how they're rule compliant. So this is our diagram. It's been updated a little bit since this, but this one still gets the main ideas across. It's got a lot on here. It'll definitely take some time to be able to digest all of this, but hopefully as a start, we can walk through this together and start going over things. So when you walk up to the car, the first thing that you do is plug in the GLV master switch. So what that stands for is grounded low voltage, and that's basically the entire low voltage system. Our chassis is our low voltage ground, so that's sort of what it's referring to, but it refers to everything low voltage on the car. So there's two keys on the side of the car, which you can see in this master switch panel in the middle. Our grounded low voltage master switch will connect the low voltage 24 volt battery. And that goes into the LV PDB, which is the low voltage power distribution board. Now this board, I actually have a personal connection. This is what I worked on my first semester. So if you have any questions about that, come and ask me. But this takes care of power monitoring, distribution, and safety to the entire vehicle. So it's checking for under voltage on the low voltage battery, over voltage, over current on the low voltage battery, as well as over temperature and under temperature on the MOSFETs that are controlling the switching of this supply into the system. Now, from this, power goes to a couple different places. I'll go through the minor ones first, and then we'll stop at the major one. So the minor ones are the brake light. The LVPDB is actually the board that receives the CAN message about whether to turn the brake light on or off. And then you have the water cooling pump, which goes through, I believe it's the motor, the inverter, the radiator, this coolant pump. And I believe this year we're actually adding a swirl pot to reduce some of the air bubbles that were in the water loop last year. If you're interested about that, I know John's been working a lot about that, and I know Weston knows a lot about it, about what the purpose of swirl pot is, and all the R&D that's gone into that. This also powers the high voltage battery cooling fans. So basically the accumulator fans aren't powered off of the battery. They're powered off of the low voltage because they pull so much current, and we didn't want to design a high voltage to low voltage DC-DC converter that had this high of a current limit. It would have been a difficult engineering task, and we wanted to spend our time elsewhere on the development of this vehicle. Maybe in the future, that's something we go towards, but for now, it's powered off of the low voltage bus. And the radiator fans. Like I mentioned before, we're powering the pump, that puts all the liquid through the coolant loop. But the radiator, when the car is not going fast enough, there's actually not enough air going through the radiator because the car's speed is what determines the airspeed through the radiator. So we actually have these fans to pull air through the radiator when we're not going fast enough. Is there any, and then the final one that I said I would end on is the CAN bus. So throughout our whole car, we have a Cat 5e cable going with RJ45 crimps on the end. And that has 4 twisted pairs, and we use 2 of those for 2 separate CAN buses. That's so that we have a high enough data bandwidth for all of the sensors on the car. And the other 2 twisted pairs, one is for power and one is for ground. And sort of this daisy chain system of CAN and power is how we get information and energy across the entire vehicle. So is there any initial questions about this system?
Uh, yeah. Hey, Andrew. So, um, I'm supposed to be working on the brake light,
Hmm.
and you said that's controlled, like turning on and off the brake light is controlled by the CAN bus.
Yeah.
Um, so when I'm designing the circuit, uh, like first of all, I have 24 volts powering the board, right?
Hmm.
Um, but then what um do I need to have like an STM32 on that as well to like receive CAN messages and turn on and off the brake light, or how exactly does that work?
Yeah, so the initial intention with this system was to make it as simple as possible. So actually, you don't need all of that. What it looks like is, here, I'll draw it off to the left side. So we have this bar, and let's say the side on the left is LVPDB. And also, I apologize for my slow drawing. I'm using a trackpad right now. Um, and then on the right side, we'll have brake light. And there'll be like some harnessing in between, right? But the way this works is we're actually getting our plus 24 from over here, right?
Yeah.
And this goes out to the brake light. And then the brake light isn't just one LED. It'll be an array of LEDs in parallel. But for our purposes, I'm just going to draw one so you get the general idea. So we have that LED, right? And then it actually goes back into here. And the way we have this set up is actually a MOSFET to ground. And then this gate goes to an STM32 pin.
I see.
So that is how the logic is done. It's the STM32 on the LVPDB. The initial reasons we chose the LVPDB to do this is because it's one of the, on SN1, it was actually the only low voltage circuit in the rear half of the car. So it's really just proximity. And then also it already has the power rails. So it's pretty easy to pull it off of there. But yeah, you would have more LEDs in parallel if you wanted a brighter brake light.
Okay, so I wouldn't need to worry about like the MOSFET or any of that other stuff, right? Because that's done by the like low voltage like power distribution board.
Yeah, no, it's simply just the harness from the LVPDB. How
Mm,
does that harness go into whatever housing you have?
yeah,
And then inside of that housing, how many LEDs do we need to meet the brightness requirements of the rules? It has to be visible in daylight.
yeah,
And then biasing those LEDs because actually there's one component that's missing here, right? When it comes in, you actually put like a resistor there, and
yeah.
then it goes through the LED so that the proper voltage drop can be on the LED. So basically, how do you bias that?
Okay, I don't want to make this all about my project, but like since I'm already asking, like you said the LEDs are going to be in parallel, but like I started working on my like the LED array, and like what I have right now is like I think either 4 or 5 rows of LEDs that are in parallel, but in those rows I have like each row has a resistor, and then each row also has like 3 or 4 LEDs. Is that like in series? Is that like kind of how
Yeah,
things should
so
be? Okay.
that could be plausible. We'd have to look at how much current you're going to have going through each of these columns if you decide
Yeah.
to stack multiple LEDs, because it will be dimmer the more you put. But yeah, that's definitely something we should talk more about offline and
Okay.
do like a design review or sort of walk
Right.
through the math you've done for that.
Hmm.
But yeah, these are all good questions to be thinking about.
Okay. Thanks.
A quick question on the Cat5 cables.
Yeah.
So you said um 2 pairs are for CAN, 2 pairs of the twisted wires. Okay, and
Yes.
then one of the other pairs is for, you said that was power?
Yeah, so we have one twisted pair is plus 24 volts,
Oh,
and then the other twisted pair is ground.
okay. Um, is that like kind of like power over Ethernet, or is that the same thing?
Yeah, so there's a lot of different classifications of power over Ethernet. The one that people typically think of, and the one that is like actually power over Ethernet,
Yeah.
is all four twisted pairs are used for communication and for power delivery. So you're actually
Okay.
communicating on the same wire as you're delivering power, and then you're sort of filtering out the communication and using power. Um,
Oh,
this
okay.
it's a little bit confusing, the classifications. When I looked it up, we're technically doing like it's like version 1 or something, or version like 2A.
Oh,
Um,
okay.
but this is not what power over Ethernet is nowadays.
Oh, okay. Okay. Got it.
All right, I see a question in the chat. The master switch is just the key for low voltage. Yes, that is correct. So it's basically just shorting this red arrow before that goes straight to the 24-volt battery to the red arrow after. It's either just open and then you twist the key and it shorts. And when you twist it and it's shorted, the key doesn't come out anymore, but it is removable in the off position, and that is a part of the rules. Oh, sorry. Evan did this slide deck. Here's the actual, okay, I'll make sure to do this for the rest of them. So as you can see on the car, the red box is where the master switches are. Um, this is the key that turns on all low voltage systems, which is basically most of the PCBs. It connects the 24-volt drill batteries to the LVPDB. Oh, yes, very important. Hopefully you all learned about the tractive system active light during the high voltage training. But if low voltage is off, that light doesn't have power. So you want to make sure that whenever you're working with the car, low voltage is on so that you can make sure that that light is solid green, which means the tractive system is not energized. You never want to be like working on the car or touching it if the tractive system is energized, i.e. the red light is flashing. That's not a safe state to be like touching the car and working on it. So you want low voltage on to make sure that it's green and it's like safe to work on. Oh, and then LVPDB, it used to step it down from 24 volts to 12 volts, but we're trying to limit it to just being 24 volts now. Also, these yellow arrows in the diagram are the shutdown circuit. That also should have been gone over at the high voltage safety, or maybe it wasn't this year. And if it wasn't, we'll circle back on that and we'll go through that in a different presentation. Okay, so this presentation splits up the LV system into sort of 3 parts. So the first part is the APPS, or the accelerator pedal position sensor. So what this does is it takes all these sensors, the dark gray boxes down here, and puts them into a PCB with a microbasic on it so that we can read all these signals, put them onto the CAN bus, and do some logic with them, as well as pass on the analog signals to the BSPD for it to do its safety features, which I'll talk about in the second third. So the sensors it takes in are accelerator sensor 1, accelerator position sensor 1, accelerator position sensor 2, brake position sensor, and then there's front brake pressure and there's rear brake pressure. For those of you that didn't know, there's actually different cylinders on the brake pedal. One of them actuates the front tires or the front brake calipers, and the other one actuates the rear, because you actually sometimes want to like shift the pressure between the two so you can control like how much you go down or like how much. There's a lot of vehicle dynamic stuff that I'm not completely familiar with. But basically, something that I didn't know that's actually important for this distinction is formula brakes in general, and this goes from Formula One all the way down to FSAE. They don't really move, so there's not much movement on them. It's really sort of a pressure transducer, or not a transducer, but like a pressure transmitter. So you sort of just push on the brake, and how much pressure you're pushing translates to the brake calipers, because you have hydraulic fluid in there, so it doesn't compress. So that's why brake pressure is important, because the brake's barely moving. The brake encoder is meant for some testing with like figuring out how we want to do regen controls, which is a whole other topic that we can dive into really deeply if you guys are interested, but that's a completely different conversation. So the APPS is up here under the hood of the car, around where the pedals are, that makes sense. And the simple torque command that we had in SN2 is if the pedal is not pressed, it's 0. If the pedal's fully pressed, that's max torque. And then we just did a linear mapping. That's updating a little bit so that we can actually optimize for maximum power as opposed to just linear torque command. But if you're interested in that, you can talk to Evan, who was working on that. He's on an internship now, though, so I think Malika is doing the lead on that. So is Shamila. So those two are also good people to talk to. And so we take this torque command, and that torque command is read by the microbasic on the APPS, and then it sends or it reads the sensor position on the APPS, has a command torque function that goes into, and the output is how much torque you should command. That goes onto the CAN bus, and then the inverter or the motor controller reads that, and then that is what does all the actual high voltage commanding of the motor. Is there any questions on accelerator pedal position sensor? All right then. The next one is BSPD, or brake system plausibility device. This is very adjacently related to the APPS, so adjacently that we actually, it used to be like two PCBs on top of each other with just wires running between the two. But actually this year for SN3, we're switching it so that you just have the APPS and the BSPD is a shield that goes onto that, because really they require almost all the same signals. But the BSPD is actually controlling the shutdown circuit, and it's completely analog so that nothing could go wrong in software. So it's part of the rules. You have to have one of these. A lot of companies actually sell these off the shelf because FSAE is such a big community that they actually have a market for this. But we make our own, all our PCBs are custom across the whole car. So this doesn't actually have the logic for how it works, but that's the most important part. So let me go over that first. Or actually it does. So this causes shutdown if current is flowing out of the accumulator and the brakes are engaged. Now, why is this a dangerous position? Why should we shut down the car if this happens? So the reason you shut down the car is because if current is flowing out of the accumulator, it likely means that you're commanding torque to the motor. So the motor's trying to spin and the brakes are stopping it from spinning. So they're working against each other. And usually when that happens, that shouldn't be happening, first of all. Second of all, they're fighting against each other and something's going to eventually break if this condition persists. So it's just safest to activate the shutdown circuit, turn off high voltage, and just reduce the risk. The actual rules specify it as 5 kilowatts have to be coming out of your pack, I believe. So basically, you just do the math for what your pack's nominal voltage is, figure out how much current that would cause, and then that's how we set the current sensor that's in the high voltage box to measure. So that's an additional detail that, sorry, I skipped over that at the beginning. We have our high voltage box in the back. I think that's going over later, but that has a current sensor in it that routes how much current is coming out of the tractive system to the BSPD so that the BSP knows how much current is coming out. And then the BSPD does the analog sensing of like, what is my 2 set points? Am I above or below? Or if the sensor is disconnected, it just turns off in the first place. It just can't even turn on if there's not a sensor connected. Or if like your sensor signal is shorted to 0 volts, ground, or shorted to 5 volts because you messed up your harnessing, that also immediately cuts it off. And you may be asking, well, how do we know if our sensor is just at the 0 volt or the 5 volt set point? And the way you do that is you actually only set your sensor's operating point between 0.5 volts and 4.5 volts. So if you're at 0 or 5, that's actually out of range. So you keep your sensor operating point between those two, so you know 0 or 5, there's something wrong with the harnessing. And yeah, if you guys see the acronym HEX, that's Hall effect current sensor. That's the current sensor in the HV box. So I see a couple things in chat. What if the driver pushes both the brake and the accelerator pedal? Ishan, you are correct. The car takes a screenshot, just like if you press the power and the volume down button. It actually takes an image of the driver. That's how we get all of our marketing materials. Yeah, so that would be a bad condition if the driver pushed both the brake and the accelerator. But actually, as per the rules, they don't require you to shut down the car. So the shutdown circuit, what it actually does is it opens the accumulator isolation relays, which are basically just connectors that connect the battery to the car. So it just disconnects the battery, basically, pulls the plug. So competition rules actually state if you press the accelerator and the brake, you don't have to activate the shutdown circuit. Your APPS can actually just consider that an implausibility on the APPS side as opposed to an implausibility on the BSPD side. And you just don't command torque for those time steps because you can sense you're pressing the brake, you can sense you're pressing the accelerator, so you just don't command torque. You don't have to shut down, which is good, because then as soon as you lift up on the accelerator and lift up on the brake and then press the accelerator again, the car will begin operating again normally. All right, so any more questions on this section or the safety? All right then, forging forward or pushing forward. Okay, so once again, Evan made this presentation. I made this diagram, and then he made a presentation to surround this diagram. So I guess he has BBB listed under the third part of the LV system. while it is technically powered off of the low voltage, I just want to be very clear that the BBB, or the big battery board, is located in the accumulator. So the reason for that is because it contains a lot of different things, such as the battery management system motherboard, or we have a 600-volt DC-DC converter that powers the high voltage indicator light, which is actually a light that has to be on the accumulator casing that works whether the accumulator is plugged into the car or if it's just sitting on its own on a table. And that tells you if there's high voltage beyond the airs. So the reason that has to work, even if it was just sitting on a table by itself, is, let's say it's sitting on the table and for some reason the accumulator thinks, oh, I should close the airs and send high voltage out. Obviously that should never happen on the table, but you wouldn't know if high voltage was exposed. So that's why you need this light, so it indicates. Also, the IMD driver is on this board. The IMD driver just drives the indicator light. The IMD, or the isolation monitoring device, is its own PCB that we're required to buy as per competition. Every team has the same one, and you have to buy it. So that one you can't make custom, but we can go over isolation in a different lecture. I also asked you or explained it to a lot of you during recruitment, so hopefully you have some idea from there. But yeah, so basically it goes in the accumulator attic. The attic is what we call the section above the segments. So as you can see, this is a screenshot from SN2, where we had a 4x2 accumulator housing. So you had like 4 segments going in, then you had the attic above it. Now we have like 7 in a flat pack in the attic above that, just to try to reduce that Z height. So one of the main purposes is, like I said, it's the battery management system motherboard. So it talks to all the, well, really it talks to all the daughter boards, which have 2 per segment. And the daughter boards are reading all of the voltages and the temperatures through the aux boards. And we have a voltage and a temperature of every single module, and we're also able to individually balance every single module. Our system has passive balancing, so for those of you who did the BMS recruitment project, hopefully you know about that. It can cause a shutdown event if the temperatures or voltages are outside of an safe operating point, or the safe operating envelope. Aman has been doing a lot of the system or the state diagram for the battery. So he did a lot of the software on this side. So if you have more questions about how that all works, you can ask him. It causes shutdown if the current out of the accumulator is too high. It also facilitates charging and cell balancing. So that's Amal worked on that system previously. I'm not sure who's working on it now, since he's LVE lead now. It does way more than what we're about to go through right now, but this is one of the main functions. And on the next page, the second main function is IMD driver. Yeah, like I said, the IMD is, you have to buy the specific one that it's like the Bender IMD, if you guys want to Google it. It senses if there's a short circuit between the high voltage and the low voltage system. But as I have told many of you, you have like high voltage plus, high voltage minus, and then low voltage plus, low voltage minus, and those are like not the same. Like you don't want the same grounds, you want them separate. Because if you're working on the car, right, that's low voltage ground. Then let's say you like reach over and touch something on the accumulator, and something in the accumulator got shorted to high voltage plus, and you were like, oh, let's just make everything the same ground. You've just completed a circuit between high voltage minus if you made that the same as low voltage ground and high voltage plus, and now you have a circuit that goes between your arms, so it goes through your heart, and that's not good. Any amount of current through the heart is bad enough, and you can cause significant issues. So this basically monitors to see like if high voltage minus got shorted to either or if high voltage plus got shorted to either. So like if it was faulted, the car would be in an extremely dangerous state, but it should not be immediately about to like explode or something. Like it should just be like, don't touch it. But this, if the IMD trips, that does cause a shutdown event. Is there any questions on anything that I just went through? I know that that was quite a lot. The big battery board does do a lot of things beyond this as well. It's more than the 4 functions I have drawn in here. All right then. I don't see any questions in the chat either. So all of that, we just turned the first key, the GLVMS, and all of that just turned on. So now you should see the tractive system active light on. It should be green. You should be able to do any debugging that you would need to do on low voltage systems. And this is the state that you would probably, as an electrical engineer, most likely work with the car in. You would also work with the car when it's off, just to like take things in and out. Oh wait, I see a question that says, is the BBB placed inside the accumulator only because it's closer to what it's controlling? Yes, part of it is proximity, but also because it is sensing high voltage nets, there is high voltage exposed on that board. So it needs to be completely contained so that nobody could possibly touch it. And so that's part of the reason why it's in the battery pack, because that's the enclosure to protect us from all of that high voltage that's on the board. All boards with high voltage, just a note, are also sprayed with conformal coating, which basically like puts a thin layer of, I don't know what exactly the like chemical or material is, but it puts a thin layer of non-conductive film over everything so that nothing would short, or it also stops like corrosion and such. Um, but yeah, it's placed in there because it makes harnessing easier, and also there's high voltage, so it has to be contained. Yeah, so all of that just turned on with the first key. You guys are mostly working on the car when it's like turned off or low voltage. Turning on the track to system master switch should only be done when you intend to work with high voltage. So you should always be aware that turning this key, I have just enabled high voltage. And what that means is an ESO needs to be present. An ESO is an electrical safety officer, and basically there's someone who we have listed in the competition as like being able to operate high voltage and work with all those systems. If something goes wrong, their name and phone number is on the accumulator. So at competition, if someone sees the accumulator and something's wrong with it, like they call them, you know, like, hey, you need to come like fix this or get this or whatever. So certain people are authorized as ESOs. The list right now, I believe, is me, Nikhil, Smith. I think that's it for everybody that's present on campus. We're trying to expand that list a little bit. ESO is a training beyond high voltage safety training. So high voltage safety training is necessary for everybody, but there's like a level of experience and knowledge beyond that, and that's what like ESOs are for. So you should never be working with high voltage unless an ESO is present. So now if we turn the tractive system master switch, which is directly next to the grounded low voltage master switch, also the tractive system master switch should have a lock over it that only ESOs have keys to. So you guys shouldn't even be able to like fit the key in there to turn it on. Like there's a lock that cuts it off so nobody can access it. But anyway, this switch is basically just another item in the shutdown circuit. It doesn't explicitly by itself activate high voltage. It's just the last item in the shutdown circuit that you would be turning. And when you turn it, you're like, okay, everything else in the shutdown circuit is connected. Now, like connect the last thing. And then after you do that, the airs should close, the system should start pre-charging, and then you should be ready to drive. Or ready to drive is a specific state. You should have tractive system active. So, right, that red light will start flashing. It'll turn from green to red light flashing on the top of the car. Yeah, like it says here, it only does that if the rest of the car and T cell turns on. Okay, is there any questions about like the actuation or operation of the tractive system master switch? All right, then let's move on to the high voltage system. So actually, let me pause again. Just anything low voltage related. Does anybody have any more questions on what we covered, or like things that I didn't cover that you feel like should have been covered in the low voltage section? Like I said, this is not completely all encompassing. Like I'm not, as you can see on the diagram, I'm not talking about data logger. I'm not talking about the dashboard. I'm not talking about all the components in the shutdown circuit. I'm not talking about the sensor modules, which you can see at the bottom, like rear SCM, front SCM for sensor collection module. I'm not talking about any of that. We can go over that in another presentation. I just want to make sure that this presentation is a consumable chunk, not too large, not too small. So I guess including those things, if you had a question that related to this presentation, any questions about the low voltage system? All right then. Starting with the high voltage system, there's two main physical locations that you will encounter high voltage. Really four main, but two of them are like the inverter and the motor. So it's like those should not be opened. Like those should be closed systems because the inverter is like the inverter and motor are like the only two circuit components you could say that we purchase completely assembled. So you may be like inserting harnesses and stuff, but like those should not be opened. But they do still have high voltage associated with them, and you do need to be careful of that. But the two high voltage systems that we design are the accumulator, or aka like the battery pack. The competition calls it accumulator. It just uses like energy source neutral terminology. I guess so that if anybody wanted to move away from batteries, the rules would encompass that. Maybe, I'm not sure if that's why or not. That's my best guess. But the other half is the HV box, so we'll cover that after we finish this. So the accumulator is the big shiny metal box in the back. Honestly, one of the most common sayings that I feel like encompasses FSAE is we're not building a car, we're building a battery. The accumulator is honestly where the most things can/will go wrong. It's the most dangerous with the high voltage and all the safety that's required to even touch this thing, let alone open it. It has the most engineering integration required. We have an entire mechanical and electrical sub team just dedicated to this one piece of the car. And like manufacturing, like the manufacturing PM spends a lot of time on accumulator and high voltage enclosures. The chief mechie and the chief EECs spend a lot of time working on accumulator integration. Even the president oftentimes has to get all the way down into like the weeds of the accumulator and make sure that things are running. Just because we want to make sure everybody's safe, we want to make sure things work, we want to make sure the car runs, and we want to make sure the car runs well and like we can compete and place well, right? So the main parts of the accumulator, first off, are the airs, the accumulator isolation relays, and relays are basically just switches. They're basically short or open, and they connect the battery to the rest of the car. So those are labeled in the right side of the diagram in the orange blocks as air plus and air minus for HV plus and HV minus. These are physically open It's not like an electrical open or close, like these are physical metal bars inside. That's what the symbol shows. Like there's a coil that you send a current through that like physically moves a bar to open or close these. Um, so actually a really important thing about the airs and pre-charge really quickly. This presentation isn't supposed to go over pre-charge, but I'll just cover this really quickly because this is a common interview question when talking about system design for various high voltage electrical applications. So, like I said, these airs physically disconnect the battery. So you can imagine before they're connected, it's like you're plugging in the battery for the first time. We have a circuit on the high voltage box side called the discharge circuit that when the battery is disconnected, that side shorts HV plus and HV minus through a resistor to discharge a capacitor on the high voltage rail that's inside the inverter. Because, right, if you disconnected these systems and the capacitor and the inverter was just open, now your system is still energized, right? You still have that capacitor there. And if you know about how capacitors are different than voltage sources, that can actually, if you touch it, it can release a lot more current a lot more quickly. So that's actually more dangerous at that voltage, depending on how much capacity it has, how much energy is stored in it. Anyway, we can go into that more later. You have the discharge circuit. We'll discharge that. So when I plug this in for the first time, you can imagine I have 0 volts over here, and I have 600 volts over here. If I just straight up went and like connected that, I've just connected 600 volts through an empty capacitor, right? I discharged that capacitor, so it's empty. And when a capacitor is empty, it looks like a short. So I just shorted that 600 volts through like milliohms of resistance, lots of current. And that current can actually weld the airs shut. And then if you weld the airs shut, right, our shutdown circuit no longer works because if we remove power, it's been welded shut, right? This thing basically went down and so much current went through it that it like blew up, melted. Not blew up because it's still in one piece, but so much current went through, so much heat, it melted the two pieces together. So that's what pre-charge does. You can see on the top right here. It's a different switch. Actually, the slightly smaller than the airs because the current's lower, and a resistor. So the way the car turns on is you turn the tractor system master switch, shutdown circuit completes, air minus connects first, then the pre-charge switch closes, but air plus does not close. Then, as the capacitor charges through this resistor, which we can set how long that takes, right? We know the resistance, we know the capacitor and the inverter, RC time constants. We know how long this system will take to charge up. And we also have sensors on the other side to know once it's charged up. The inverter actually tells us what voltage it's at. Once that happens, then air plus closes and pre-charge switch can open, and then your car is ready to, it's charged. I'm being careful with the ready to drive terminology because that's a different state that we can go over later, but your car is charged. All right, segments. Actually, I'm going to stop for questions on airs here, just because that was a lot before I go on to the next steps, just so that we can keep moving. Any questions on airs or pre-charge system or discharge system? Okay, quick temperature check. How do people feel about the pace right now? Should I slow down a little bit, or is this a good pace? All right, we got something in the chat. Okay, pace is good. Okay. I do feel like I've been talking a little bit fast, so I'll slow down a little bit, but we can keep the pace up and keep going along. I know we had a late start in the hour, so I just want to make sure I respect your guys' time if you have anything after this. But hold on with me for a couple more slides and we're almost there. Okay, so the battery is divided into segments, and each of these segments, you can think of it as like when you put your batteries, like your AAA batteries into your remote control car, and you have to put like three, and they have the springs. Basically, you just put three batteries into series. So it's sort of like that. Each segment is one of those smaller batteries, and then we connect them up in series to build our whole system. Um, and these have maintenance plugs in between them so that if you open the accumulator, it wasn't a rule last year, it's a new rule this year. The first thing you have to be able to access when you open the accumulator is the maintenance plugs. And the first thing you have to do after you open your accumulator is remove the maintenance plugs, which honestly is that's a good rule, and it's what our operation has always been. But it's good that they put into writing just to make sure that everybody does it, and new teams who are just reading the rules like understand that's something they should do. Um, so yeah. Anything else about each segment has one aux board on it, and that's what our battery modules screw into. And then it has two daughter boards on it that communicate for 10 cells each. Last year was 17 modules on one segment. This year it's 20 modules on one segment, so 10 each. Last year it was 8 and 9, I think, each. But yeah, then those go to the BBB, which has the BMS motherboard on it. You can see how the daughter board daisy chain goes here, D1, D2, D1, D2. It goes through, and each segment is connecting to the next one. Any questions on battery segment architecture? If you want the stack up of how that looks assembled, go to the SN1 or the SN2 documentation. I think both of them have the same diagram. All right then. All right. Okay. Interlocks. Interlocks are a big one. Both physically, they are very big connectors. But also there's a lot of thought that goes into where they are, how accessible they are, like what the accessing looks like. They aren't shown on any of the photos here, but in the diagram on the far right, you can see the interlock. So, oh, and there's the Notion page for the accumulator subteam on this page, so I would definitely recommend you all go look that out. I think most of you are in accumulator as well. I think a lot of our recruits this year were accumulator EE. So definitely make sure you check that out, especially because you guys should be getting project updates there. But the interlocks are big orange connectors that they have like this black switch. You can look them up in the Notion page, and I can send some photos in Slack after. But it's big orange connector with this big black lever. And what it does is it actually has 4 terminals in it. 2 of them are for HV plus, HV minus, and then the other 2 are much smaller. They're on the top. You actually have to like look for them. They're not as obvious. Those 2 are actually shorted to each other inside of a housing. And the reason for that is when this interlock goes on and then latches down, that little short is part of the shutdown circuit. So this interlock has to be installed correctly for that piece of the shutdown circuit to be completed. And so there's an interlock that goes from the accumulator to the HV box, and then there's an interlock that goes from the HV box to the inverter. And that's sort of the 2 routes that you have to worry about. The actual decision of where interlocks are, where the HVD is, which is actually a separate piece. There's been some discussion about this year, and it's kind of moved around. So I don't want to say anything about exactly where they are on SN3, but that's something we can go through during manufacturing to show you guys where those are. Any questions on interlocks or their purpose or like anything else? All right then. Oh, okay. Hopefully he talks about the HV box in okay, Evan made this presentation and he's he was the head of E-Powertrain last semester. So I obviously that's where he went for the second part of HV system. But real quick, I'll cover HV box components just in case he didn't write about those in the next slide. So as you guys can see right here, we have discharge, which has its own switch to short those two together through a resistor. I don't know if this value is accurate for this here or not. Then there's a Hall effect current sensor, right? This is the one that I said earlier goes to the BSPD and tells it how much current. Then these two resistors right here for 15K are going to the tractive system measurement points. So on this master switch panel, next to the GLVMS, the TSMS, you have the TSMPs, and it's basically like 3 banana jacks. One is for HE minus, one is for HE plus, and one is for grounded low voltage. And during competition, they'll actually check your resistance between grounded low voltage HV plus and grounded low voltage and HV minus to make sure that everything's good. So next we have the E meter. This is actually another current sensor and voltage sensor that is given to us by the competition. So it's actually, it goes in line with the bus bar. So we actually have a fake bus bar piece that like screws in for when we want to test it. Then you take that out and put in the E meter during competition. So it senses the current going through the HV minus path. And then it also has an Anderson. There's like a wire that comes out of it with an Anderson crimped onto the end. So then we, in the HV box, have to put another Anderson that connects to an eyelet that's bolted into this bus bar. So it can sense the voltage and the current. And what it does with that is it calculates the power because there's competition rules that you can't go above 80 kilowatts of power. So this is, it logs all the data internally, and then they come up to your car after each event and they download all your data and they check you to make sure you don't go over that. There's also some things under here like the high voltage sensing fuse that leads to the T-cell driver. So the T-cell light driver is in the HV box as well. But yeah, is there any questions about the components in the high voltage box? All right then. Okay, something in chat. Okay, more of a competition question. Is the 80 kilowatt power limit usually the limiting factor on car performance in the dynamic events? Okay, so this is an interesting question. I'll give you a high level overview, but this is definitely something that we should talk about more and have a more in-depth conversation because it's really interesting, and it's not quite as like linear as that. Um, so actually, there's an event every year where Tesla hosts a bunch of different FSAE teams, and we all go to the Tesla Fremont facility. And for one weekend, there's like lectures all weekend about different FSAE concepts. I wrote up a whole bunch of notes about these lectures on Notion. It's called like the Tesla FSAE event. I'll look up the exact Notion page title for you guys. I wrote up a whole bunch of notes about it, and all the videos are on the FSAE website as well. But in one of these, they actually collected a lot of information because they have all the information from when teams submit and give their data, right? And they also have all the e-meter data, right? Like just massive, massive files. So they actually did their own little curiosity research where they looked at where teams placed in competition versus the peak power that they reached at competition. And it was not actually a perfect scale. Like sometimes the teams who had higher peak power were like more in the like 10s to 20s to like high 30s, not really low 30s. But it wasn't exactly like the more power you can pull, the higher you place that competition. I think part of that is because a big number of your competition points are based on like presentation skills, like design is a big part of your points. Um, yeah, design event, uh, judges panel is a big part. business event or cost event and then business presentation are big parts. So I think that might play into a little bit. But yeah, I honestly think driver skill slash driver comfortability with the car, because sometimes if the driver's more comfortable, they can beat out skill. And just like team integration, like a number of times can beat out the 80 kilowatt limit. Okay. All right then. So first talking about the inverter. So the inverter gets high voltage after the HV box through this interlock. It also gets CAN bus from the HV box. Controls the motor, receives torque commands on the CAN bus from the APPS, converts the DC power that we're getting from the battery into three-phase AC motor that controls AC power that controls the motor. And it does all the math to figure out how exactly to get DC to AC. And then there's some feedback from the resolver, which is the angle of the motor and the temperature of the motor, where it controls all of that. And it also shuts down if the motor gets too hot or if the inside of the inverter gets too hot from switching. Beyond that, the inverter also gets 12-volt power from the LVPDB, and yeah, temperature resolver. Yeah. Any more questions on things about the inverter? There's definitely a lot more that goes into this. There's also a lot of development on the software and control theory side. So I would definitely recommend talking to Shamila or Malika during an EECS meet if you're interested in learning more. All right then. Okay, now the motor. This box is around the tire on the bottom right, but if you just imagine looking through the tire, the motor is back there. The motor is what applies torque to the wheels. The motor has a sprocket on it that applies torque to a chain, and then we have a gear ratio between the sprocket on the chain and the sprocket on the rear drive axle. And then the rear drive axle has a differential on it. I think it's called a limited slip differential. These are all things you could ask powertrain more about. But basically, like when you're turning, your rear wheels don't go exactly the same speed, right? Because you're going like that. So the outside has to go faster. So this allows for that slip so you don't like skid. Anyway, it's really just a bunch of coils of wires that I mean, this is getting a little bit just into motor fundamentals, but basically you just have three phases and you have three sets of coils in the motor. And you can think of it as like, if my motor magnets are like at this position, then I turn on the coils at this and then it pulls it. And then I turn on the next set of coils and it pulls it. So it's basically like turn on coils, pull, turn on next set of coils, turn off my current set, pulls, and that's how it does it. It just like does that control. And that's how it spins around. The resolver attached gives the speed of this rotation, right? Because you can send the currents to make this happen, but then you need some feedback to close that control loop. So the resolver is like a magnetic sensor, so it can tell like this spinning speed where it is. I think it also can tell like position when the motor's not moving, or that might just be integrated from like start position. I'm not exactly sure. But yeah, is there any questions on the generalistics of the motor? All right then, something in chat. Does the resolver also give ground speed? No, so that's a good question. The resolver is like inside of the motor casing, so it can only give you the speed at which the motor is rotating. Your ground speed will be different than the speed that the motor is rotating at. One, because we have like a 1 to 3 gear ratio, on those sprockets to the tires, which I believe is a torque ratio. So you should be going like a third as fast as the car is spinning, but you get more torque, so you can accelerate faster. That's something that powertrain decides. But anyway, the way we get ground speed is there's also 4 wheel speed sensors on each tire, and that tells you how fast the tires are actually spinning. And then from that, you can calculate your ground speed. Now, there is some oversight there that doesn't account for like if your tires slip, which is actually something you could sense in software from your wheel speed sensor reading if you wanted to do more advanced controls. But we just take the simple like wheel speed sensor. You can do a generalistic brute force type of way just by dividing the speed that the motor is at, and that gives you a general idea of how fast you're going. But for exact, you want to know the speed of all 4 wheels, because that also tells you like if you're pulling on one side or if you're like dragging on one side, as well as if your differential's going right. So it gives you some more insight if you have all 4 points, but some teams just use one, which is also like fair. It's an engineering choice. All right, real quick, miscellaneous things that weren't covered here that we may cover in future sessions, but hopefully we'll like just, you can review them in Notion as well. We have Notion pages on all of these. The data control unit, there's a lot that goes into this. If you want to learn more, you should ask Sid. He's been working on this all last semester and doing the software for it this semester as well. So he's done everything from like schematic to PCB design, as well as he worked on dashboard, which is very closely related to this. So definitely talk to him to learn a lot. It logs all of the CAN messages sent over the CAN bus into an SD card that then we can read later. Super useful for debugging. And this is probably like the most important board for car improvement year over year, because you need to get every single piece of information you can off of the previous car in order to know how to improve it for the next one. Some things it collects is battery voltage and current, motor speed, commanded versus measured motor torque, which actually is where we found a big issue last semester. You have the number of Newton meters, right, that the accelerator actually commands, but how much torque is actually getting to your tires? And there's actually a big discrepancy there, which we can go more into. But yeah, you want to make sure that the measured torque, which is something the inverter can give you, which is basically like feedback torque, is you want to optimize that to get as close to your commanded. It also does coolant temperature. This is not present on SN2. It ran into some development issues. So that's why we're trying so hard this year to make sure that this thing gets all of the attention it needs and deserves, and that we'll be able to get the most improvement as possible. We were able to collect some, like a good majority of data on SN2 by different means, which we can go into in a different time. But yeah, any questions on data logger? All right. Other things that you should go through. Shutdown circuit. Hopefully this was covered at the high voltage lecture. If not, we can circle back about that and do that presentation for you guys. How the CAN bus works. You should go and see the communication protocols lecture. I probably won't be redoing that one this year, since that was the first one we posted on YouTube. So go to that YouTube video and watch that. Really good. I think I told a lot of you to watch it during recruitment. But for those of you who I didn't, you should definitely go and watch that. And the sensor data acquisition boards, Krishna is working on those. So if you have questions, you should talk to him. But yeah, that's something we could go more in depth on, like in a future date. So with that, reaches the end of our presentation. Thank you guys for coming to the second EECS education. I guess before we sign off for today, does anybody have any last minute questions? All right, all right. If you have any more questions that you think of later, please make sure to Slack me or put it on that thread in the education channel. And definitely don't just have to ask me or take my word for it. You guys can also ask anybody else during Eeks Meet. And yeah, definitely. Hope you guys all learned a lot, and I'll see you at the next one.